Kmax this morning. I want to welcome all students to this lesson. This is our second lesson on photoelectric effect, and my name is Mr. Vincent. We are going to learn a couple of things here, and to start with, we are going to look at light energy and quantum theory. Now, previously, you have learned or you have known from Form 1 that light travels in a straight line. And if I ask you to draw light, most of the time you draw light using a straight line like that, and then you put an arrow on it. Now, who says that light is supposed to be a straight line? Where did this come from? This is a postulate. This is a postulate that was advanced so many years back. At first, light was thought of as a continuous wave of energy that travels in space. But things changed when a German physicist known as Max Planck, made a discovery in 1901 about light. Max Planck was a theoretical physicist, and he came up with an idea about light, that in as much as we think that light is a continuous energy that travels in space, he debunked that postulation and came up with a finding that light travels in small packets called quanta. A packet, another packet, another packet, another packet. Small packets called quanta. That is what constitutes light. Now, energy that light have, we learned in the topic electromagnetic spectrum when we are looking at radiations. We learned that there are several radiations ranging from visible light, UV radiation, X-rays, all those ones are light. And each of those lights have energy. The energy that light have is contained in this small packet. And we have said that these small packets are called, each one of them is called quantum. Now in plural, we call them quanta when they are meaning like 1, 2, 3, these are quantum. Now, the energy contained in one quantum, like this one, energy present inside, the energy of light is carried inside the quantum. And the energy present in a quantum is called photon. Energy present in a quantum is called photon. Now, one photon of energy, if you want to find the energy that is equivalent to one photon, then you use this formula. Energy is given by H times F, where this H is the Max constant, Planck's constant, sorry. It is a constant that he gave that we should use if it is multiplied by the frequency of the light, then we get the energy that is present in one quantum. One photon of energy present in one quantum. So, up to that, I want us now to practice calculating the energy of light. So as we all know that in electromagnetic spectrum, we say that the frequency of light increases as you move from this end to the other end, whereby in the middle here we have visible lights. Visible lights. Now from this end going the other way we have UV, then we have X, then we have gamma. This side we have the radio wave, we have the micro, and then we have the infrared. The energy of a radio wave cannot be the same as the energy of UV or even X-rays or gamma rays. Now, we learned that the frequency of the gamma is the highest frequency, and that is why you see the wavelength is very small. So, the frequency here is high, while the frequency this side is low. But we are seeing that energy contained in light is given by H, you multiplied by frequency. H is a constant. So that therefore means that if the frequency is high, then light of high frequency has high energy, but light of low frequency has low energy, because they are directly related. Energy is directly related to frequency. So I want us to calculate energy contained in light in light of different frequencies. I'm going to write a question here on the board, and from where you are, you can practice. I want you to calculate the energy present in light of the frequency that I want to give. So write down this question. Red light has a frequency red light has a wavelength of 7.0 by 10 power negative 7 meters, while violet light has a wavelength of 4.0 by 10 power negative 7 meters. Compare the energy contained in red lights and that in violet lights. So take H, which is Planck's constant, to be 6.63 by 10 power negative 34 joule second is the unit of the Planck's constant, and take C, which is the speed of light, to be 3.0 by 10 power 8 meters per second. So this question, we have been given the wavelength instead of the frequency. As the formula that we are going to use, we said that energy contained in light is given by H multiplied by F. But we don't have F, instead we've been given wavelength. So we are going to find, first of all, we are going to find frequency. Given wavelength, we are going to use the first wave equation, and I hope you can remember the first wave equation. The first wave equation is V is equal to F multiplied by, where V is the velocity. Now in this case we are talking about velocity of light in vacuum, and whereas we are talking about velocity of light in vacuum, now V becomes C. So instead of V, we are going to put here C. Velocity of light is equal to frequency times wavelength. All these lights, they form part of the electromagnetic spectrum, and one property of the electromagnetic spectrum is that they travel in space at a speed of light, which is 3.0 by 10 power 8 meters per second. So using the C that we have been given and the wavelength that we have, let us calculate frequency. So for red light, what is the frequency? What is the frequency? Frequency will be given by speed of light divided by wavelength. So speed of light is 3.0 times 10 power 8, and wavelength of red light have been given here 7.0 times 10 power negative 7. Now if you work out this, what do we get? Work out that, what do you get? If you've gotten the answer, you can post it on the comment section. If you've gotten the answer, you can post it on the comment section. Similarly, violet light, let us also calculate the frequency of violet light by taking C over wavelength. So you can go ahead and substitute wavelength. Our violet light is given as 4.0 times 10 power negative 7. So for violet light as well, once you have used your calculator to work this out, So the first one gives us the frequency here is 4.286 times 10 power negative 14. Sorry, times 10 power positive 14 has, every time you are writing a decimal number, you ensure that you maintain 4 significant figures. 1, 2, 3, 4 significant figures. At the second one, you get 7.5 times 10 power 14 as well. Has. Now look at these two frequencies, the frequency of red lights and the frequency of violet light. You realize that violet light, red light had a wavelength of 7 by 10 power negative 7, while violet light had a wavelength of 4 by 10 power negative 7. So this wavelength was much bigger than this one. This one is 7, and this one is 4. The wavelength here is higher than this one. Now the higher the wavelength, you now realize the frequency is small. The frequency is small when the wavelength is large. When the wavelength is small, the frequency is high. And we have learned that energy is given by H times frequency. So let us calculate the one for red light. Energy of red light. Then this side we are going to calculate energy of violet light. Let's see. So for red light energy, we are told to use the Planck's constant here, H, which is equal to 6.63 times 10 power negative 34. Always use the Planck's constant that is given to you. Planck's constant can be given together with the equation at the end. Immediately at the end of the equation, you can be given the Planck's constant. So you don't have to cram Planck's constant. But sometimes, when it is an exam situation, Planck's constant is given at the cover page, page 1. Under the instructions to students, towards the end of the instructions to students, you find Planck's constant has been written there. So you always check. Don't assume that Planck's constant is always 6.63 by 10 power negative 34. Sometimes you can find that it is 6.64 or 6.65, depending on what is written there. So that is what you use. So Planck's constant is 6.63 by 10 power negative 34. Then we multiply by the frequency of the red light. We've calculated the frequency of the red light to be 4.286 times 10 power 14. Power 14. I don't think this space will be enough. So if you work out this one, what do you get? If you work out that, what do you get? Work it out in your calculators and put your answer in the comment section. So We've gotten something like 2.842 times 10 power negative 19 joules. So that is the energy contained in one photon of red light. One photon of red light. One photon of red light contains that amount of energy. The energy now is in joules. Now what about violet light? Violet light. Energy contained in one photon of violet light is also given as HF. So we're going to use 6.63 times 10 power negative 34 times the frequency of violet light, which we got here 7.5 by 10 power 14. During substitution, when you are writing, you don't have to write joule second and hertz. We simply write the numbers that we are going to multiply without necessarily writing the units, but at the end of the calculation, that is when we write the unit for energy. Energy is measured in joules, so the unit, of course, becomes joules. So if you multiply that, what answer do you get?
4.973.
So you get 4.973
times 10
by 10
negative 19
power negative 19 joules. Now, look at these two energies. Between one photon of red light and one photon of violet light, which photon contains more energy? Which photon contains more energy? So are you capable of comparing this number and this number here? Which one is bigger? Which one is bigger? So this is, remember both of them are times 10 power negative 19. Now this one is 2.842, and this one is 4.973. Of course this one is bigger. So that therefore means that violet light contains more energy. Violet light contains more energy. So one photon of violet light contains more energy compared to one photon of red light. So the question was asking us to compare the energy contained in red light and that in violet light. So what is our answer? Violet light contain more energy. Violet light contain more energy. So one photon of violet light contain more energy. So up to this point, we are learning that energy of light varies depending on the frequency of light. The higher the frequency, the higher the energy contained in the light. Upon the discovery of the energy contained in light, after that discovery of the energy contained in light, another physicist came into scene known as Einstein. I know you want to ask, he only had one name. No, he didn't have one name, he had two names. He was called Albert Einstein. Albert Einstein. Albert Einstein worked with Max Planck for some time, and his discovery was also interesting. He tried to explain photoelectric effects in terms of quantum theory. What happens exactly during the photoelectric effect? Previously, you have learned that when light of sufficient frequency is directed onto a metal plate, the electrons are ejected out of it. Now, Albert Einstein tried to explain what exactly happens so that the electrons are ejected. And this is what he said. I'm going to demonstrate by the help of a diagram. Electrons, some of the electrons are always near the surface, some are deep under inside the metal, some are near the surface, some are deep under, and so on and so forth. These are electrons. When a radiation is directed onto the metal, when light is directed onto the metal, and this light is a monochromatic light. Monochromatic light. I hope you can remember what monochromatic light means. Light of one particular color. If it is red light, if it is blue light, if it is violet light, that is called monochromatic light. Now, when light of one color is directed onto a metal plate, and it happens that the frequency of the light is maybe too low, then it means the energy contained in that light may not be sufficient to eject the electrons out of the metal. Because remember, energy contained in light is given by H times H. Now, if this frequency is low frequency, Albert Einstein demonstrated that light of very low frequency is not capable of ejecting the electrons. The electrons don't come out. And that means photoelectric effect does not occur when the frequency of light is very low. However, when we direct light of fairly high frequency, light, then it is noted that for high frequency light, the energy is now high. The energy frequency is high, therefore the energy is now high. So the electrons are ejected. And then they come onto the metal surface. Why are they not going away? They won't go away until they get more energy to push them away, to break them from the forces of attraction of the photons which are within the metal. Remember, these electrons are on the orbitals around the nucleus. And the nucleus of an atom is positively charged. The positive charge on the nucleus of the atom is what is attracting these electrons to the metal. So it is until the energy is high enough to break them free from the attraction of the nucleus, that is when they will fly away. So if the frequency is high, but not high enough, the electrons will be ejected from the metal, but then they come and reside on the surface of the metal. They don't go away because they are still being attracted. If we now decide to use light of very high frequency, light of very high frequency, the energy here is now going to be very high because remember frequency is very high. Now energy is going to be very high. Now the electrons are going to be ejected onto the metal surface, and then they will fly off. They will start flying off out of the metal. See that? So the energy in this case will be used to do two things. One will be used to eject electrons until they reach the metal surface. And then after they reach the metal surface, then part of the energy will now be used to lift them off the metal surface, to provide kinetic energy to the electrons so that they fly off. So what are we saying? We are saying that the photon of energy of light directed onto a metal plate will do two things. One, part of the energy in that photon will be used to dislodge electrons, to dislodge. What is to dislodge? To remove electrons from the metal until they come to the metal surface. So part of the energy will be used to dislodge the electron, the energy of light. Part of it will be used to dislodge the electron, and then the remaining part of the energy will be used to provide kinetic energy to the electron so that they fly away. That is what Albert Einstein came up with. Albert Einstein. And now because of that, I'm going to write that in words. So Albert Einstein said that one photon energy energy contained in one photon of light is used to do two things. One is used to dislodge an electron from the metal. Up to the surface. Up to the surface of the metal. And then part of the energy is used. Part of the energy is used to provide kinetic energy to the dislodged electrons. Now they are able to move from the metal surface. Yeah? And one photon of energy is given by the formula E is equal to hf. So the energy contained in one photon is used to do two things. To dislodge, there is part of it which is used to dislodge the electron from the metal surface, and then there is part of it which is used to provide kinetic energy to the emitted electrons. To provide kinetic energy to the emitted to the ejected electrons, provide kinetic energy so that they move away. Now, this part that is used to dislodge electrons until they come to the metal surface, energy used to dislodge electrons until they come onto the metal surface, that energy is known as work function. So this part, this energy here, we call it work function. Work function. Work function. Work function. And the frequency of light that produces this amount of energy that is just enough to dislodge electrons. The frequency of light that produces enough energy just sufficient to dislodge electrons. This frequency has a name. The frequency that produces the energy just enough to dislodge electrons, it has a name. What do we call this frequency here? We call it threshold frequency. Threshold frequency. Threshold frequency. Threshold frequency. Denoted by F with a subscript small o. Subscript O. We call it F naught. Threshold frequency is denoted by F naught. Anytime you see F naught, then you know that is threshold frequency. What is threshold frequency? Threshold frequency is the minimum frequency of light required to dislodge an electron from a metal surface. The minimum frequency of light required to dislodge an electron from a metal surface, that is called threshold frequency. So, we have seen that when we take threshold frequency and we multiply by Planck's constant, threshold frequency times Planck's constant, what do we get? The amount of energy that we get has now a name, and it is called work function. Work function. Work function is denoted by capital W with subscript O. So work function is equal to Hf naught. Work function is equal to Hf naught. Work function can also be denoted by a letter that looks like that. If you see something like this, don't be worried. That is work function. That is what we are calling the work function. It still can be written like that. Work function. So the energy of a photon is used to do two things. One, to dislodge an electron from a metal surface, and that part of the energy that is used to dislodge the electron from a metal surface is called work function. Then the remaining bit of energy is used to provide the kinetic energy to the electrons so that they move away. So, do you remember the formula for calculating kinetic energy? The formula for calculating kinetic energy. Kinetic energy is given by a half mv squared. A half mv squared. That means kinetic energy of the emitted electron will be given by half multiplied by mass of an electron. So when I write me, this subscript e simply means mass of an electron. Mass of an electron times velocity of the electron squared. This is the formula for calculating the kinetic energy of the emitted electrons. So don't think that this m and this e are two different things. No, when we write it like this simply means mass of an electron. And mass of one electron. Mass of one electron. Do you know it? The mass of one electron. The mass of one electron. An electron is very light. So its mass, you are not expected to cram. You will always be given, anytime you are required to use it, you will always be given that in the question paper. But the mass of an electron is 9.11 times 10 power negative 31 kilograms. Negative 31. Negative 31 kilograms. Very light. So now let us combine these two so that we get the correct equation here. According to Einstein, energy of a photon is used as work function and is also used as kinetic energy of the emitted electrons. So energy, work function is given by what? Hf naught. Kinetic energy is given by what? Half mv squared. And I said that we put subscript E to show that it is mass of an electron. So to distinguish this energy from this one, the E here we learned from the start that it is given by Hf. Energy of a photon is given by Hf. So Hf is equal to Hf naught plus a half mv squared. This equation, it is just one equation written in three forms. This equation here, whether you take the first, whether you take the second, or whether you take the third, it is the same equation. This equation is what we call Einstein's equation of photoelectric effects. This is what we call Einstein's equation of photoelectric effect. So if I ask you students to write down Einstein's equation of photoelectric effect and explain its parts, what will you do? What will you write? You simply write any of these three. So you can see it has three parts. The first part is this side. The second part is this one, and the third part is that. So what does this mean? This means energy of a photon, which is given by Hf, is equal to, the second part is the energy used to dislodge an electron from a metal surface, which we are calling the work function. And the third part is the energy that is used by the emitted electrons as kinetic energy to make them fly off the metal surface. Now, up to that point, I want us to apply Einstein's equation of photoelectric effect in performing numerical calculations. So I'm going to write an example on the board. And then I want you to apply Einstein's equation to solve this example. So example, you write down the minimum frequency of light. The minimum frequency of light that can cause photoelectric emission, that can cause photoelectric emission from potassium surface. Potassium is a metal, from potassium surface is 5.37 times 10 power 14 as. This is the second time you are realizing that frequency again is to a power of 14. Frequencies, most of them you'll be finding that they have a power of 14. Power 14 has power 14, power 14. Now, when the surface is irradiated, When the surface is irradiated, using a certain source, when the surface is irradiated using a certain source, photoelectrons are emitted. With a speed of 7.9 by 10 power 5 meters per second. Calculate A, the work function of potassium. The work function of E. The maximum kinetic energy of the emitted photoelectrons. The maximum kinetic energy of the emitted photoelectrons. And C, the last one, C, the frequency of the source of radiation. Good. So, whatever you are, look at this question. The minimum frequency of light that can cause photoelectric emission from a metal from potassium surface is 5.37 by 10 power 14. Minimum frequency is this one. So what did we call the minimum frequency of light that can cause photoelectric emission? We called it threshold frequency. See, we wrote here that threshold frequency is the minimum frequency of light required to dislodge an electron from metal surface. So what we have been given here is threshold frequency. This one is now the threshold frequency. F naught given. We continue the question. When the surface is irradiated using a certain source, now the surface of the metal, when it is irradiated using a certain source, photoelectrons are emitted with a speed of, so this, what is this? This is velocity of the emitted electrons. Now, calculate work function. So the question which we are being asked, we are going to see how it is calculated from here. From Einstein's equation, we learned that energy of a photon is used in two parts. One, to dislodge electrons, and two, to provide kinetic energy. Now, in the first part, we've been given the work function F naught. And we are asked, we've been given the threshold frequency F naught, and we've been asked to find the work function. So, work function is given by H F naught, isn't it? What about this other side? This other side will be given velocity. So when we have velocity and we have the mass, we can also calculate this part, isn't it? Then when we add the two, then that will give us the total energy of the photon. And the total energy of the photon is given by Hf, therefore we can be able to get F. So let us work out the first part. First. First part, the work function. Work function is equal to H F naught. So, if you can remember what was our H in the previous question, it was 6.63 times 10 power negative 34. We multiply by F naught, which will be given here as 5.37 by 10 power 14. Now if you multiply that, what do we get? multiply that, what do you get? You can drop your answer in the comment section for those who are watching us online. I can see most of you are getting it right. You got 3. Those are on the ground. I'm waiting for those who are video. You got 3 points. 3.5, 6, 8, 3.560 times 10, of course, power negative 19. Times 10 power negative 19 joules. Now you realize that even in the previous question, when we are calculating the energy, we just found some number times 10 power negative 19. So that means most of the time when you are going to calculate energy in joules, you will always find that the answer is times 10 power negative 19. Such that if you multiply and you find the answer to be times 10 power negative 54, all power negative 63, all power negative 43, then you just go back to your calculator and introduce brackets and ensure that you work it out properly. Most of the time, you will realize that maybe there is something you have not done properly in the calculator to get the answer. Energy, you realize the answer is always times 10 power negative 19, not power positive, power negative 19. So that is the first part. We go to the second part. The second part asks us, calculate the maximum kinetic energy of the emitted photoelectrons. So, kinetic energy, maximum should not surprise you. Maximum should not surprise you. Why are you asked maximum? We also have minimum. Now, when you are asked maximum kinetic energy, it is important for me to tell you that when the electrons are emitted from the metal surface, not all the electrons not all of them travel with the same energy. Some travel with slightly lower energy compared to others. Now, we want to find the one which travels with the highest energy. What is its maximum kinetic energy? That is why we put here maximum. So, maximum kinetic energy will be given, the formula for kinetic energy is just a half times mass times v squared. So, a half times mass of an electron. Do you remember the mass of an electron? Yes, it is still on the board. 9.11 times 10 power negative 31. So that is what we are going to use for this one. Times 10 power negative 31 times the velocity of the electrons we were given as 7.9 by 10 power 5. 7.9 times 10 power 5. But remember this velocity we are supposed to square. We are supposed to square it. So don't forget to square. Most of the time students forget to square it. We're going to square it. So it is very long. Fill it in your calculator and drop your answer in the comment section. If you work out this, what you get? You should get something like 2.842 2.843 times 10 power negative 19 joules. If you have gotten that, then I think you are correct. If you have not gotten that, then you need to go back to your calculator and check again. You should have gotten something like 2.843 times 10 power negative 19 joules. So if you don't know how to key this one in your calculator, you simply dial in your calculator 0.5 times 9.11. Then you go to EXP. Near the equal mark button at the bottom of your calculator there is a button there written EXP. You press it and then you press negative 31. Then you press 7.9 EXP 5. Then again 7 times 7.9 again EXP 5. You press equal mark, and that will directly give you this answer. So that is how we calculate the maximum kinetic energy of the emitted electrons. Is calculated like this. You've gotten the answer there. This is the maximum kinetic energy of the emitted electrons. And then the last part, the frequency of the source radiation. The frequency of the source radiation. Frequency of the source radiation. So for us to calculate the frequency of the source radiation, we said that energy of the radiation was used in two parts. The first part was work function, and the second part was providing kinetic energy. We have gotten the work function to be 3.560, and we have gotten the kinetic energy to be 2.843. All this is times 10 power negative 19 joules. Now let us add them so that we get the total energy. So the total energy will be, if we add this, what do we get? Should get 6 points. So we are adding this energy plus this one. That is the work function plus kinetic energy, so that we get the total energy of the radiation.
3.03.
6.303. 6.303. Thank you so much. Those who are with me at home and are really busy with their calculators, calculating and placing the answer in the comment section. God bless you. you are good students, always times 10 power negative 19 joules. Now this is the total energy. Yes? 303, yeah? 403. Okay, 403, good. 6.403 by 10 power negative 19 joules. That is now the total energy contained in one photon. And how did we say we calculate energy in a photon? Energy in a photon is F. So the energy in the photon is this. We want to find the frequency of the radiation. This frequency here now. This energy we've gotten, you want to calculate frequency. So how do we use this formula now? We divide both sides by, we make F the subject. So we divide by H. So we are going to find F is equal to energy divided by H. So the energy of the photon is 6.403 by 10 power negative 19 divided by H, 6.63 by 10 power negative 34. This one is joules, this one is joules second. So, of course, frequency will always be Hertz. Frequency will always be Hertz. So if we divide that, 6.403 divided by 6.63. You get 9.658. 9.658 times 10 raised to power 14 as 9.658 times 10 raised to power 14, as you see that. So this was the frequency of the source radiation. That was the frequency of the source radiation. Good. Now, before we go for a short break, I want us to do two things. I want us to do two things now. One, I want us to define two terms here. The first one, work function. Work function. I want us to define this term, work function. What is work function? So we already know that work function is we said that the energy of a photon is used in two parts. The first part is to dislodge electrons onto the metal surface, and the second part is to provide kinetic energy of the emitted electrons. So the part that is used to dislodge the electrons from metal surface, we call it work function. Now, how do we define work function? How do we define work function? If I ask you to define work function, what should you do? How do you define it? What do you write? Work function is the minimum amount of energy. The minimum amount of energy needed to dislodge an electron from a metal surface. the minimum amount of energy needed to dislodge an electron from a metal surface. Remember, threshold frequency, we also said it is the minimum frequency of light required to dislodge an electron from a metal surface. Now, the only difference between threshold frequency and work function is that threshold frequency is the minimum frequency, while work function is the minimum energy. Threshold frequency is the minimum frequency required to dislodge an electron from metal surface. Work function is the minimum energy required, of course required by a metal, to dislodge an electron from its surface. Now, the second term I want us to define is threshold wavelength. Threshold wavelength. For us to define threshold wavelength, we noticed in our first calculation, in example 1 that we did, that when I get red light having a wavelength of 7.0 times 10 power negative 7, and violet light had a wavelength of 4.0 times 10 power negative 7, we found out that the frequency, corresponding frequency for the red light was being 2.8, while the corresponding frequency for violet light was being, was it 4.9? Something like that. So, whereas the wavelength is large here, the frequency is small. And whereas the wavelength here is smaller, the frequency is high. So what happens between these two? Whereas we define threshold frequency as the minimum frequency. The minimum frequency of light required to dislodge an electron. Now when we come to threshold wavelength, we talk about the maximum wavelength of light that is required to dislodge an electron. So threshold wavelength is the maximum wavelength of light needed to dislodge an electron from metal surface. Needed to dislodge an electron from a metal surface. Finally, I want you to write down this question. You attempt it over the remaining minutes, and then in our next lesson we are going to start by finding out what you obtained. Actually, you can drop your answer. Once you've calculated it, you can drop your answer at the comment section before the end of the session. So I want you to write down the third example. This was example 2. So I want you to write example 3. So write down example 3. wavelength of a photoemissive surface is 0.45. What is this? When I write something like, what is this? Something like a U with a tail. What does that mean? It's like this. A U with a tail. This one means, it doesn't mean micro. Micrometers. So micro usually means times 10 power negative 6. Whenever you see it, it means times 10 power negative 6. Anywhere you see it is times 10 power negative 6 micrometers. So 0.45 micrometers. Calculate its threshold frequency. Its threshold frequency. Calculate its threshold frequency. So you are given threshold wavelength, you are asked to calculate threshold frequency. I'm going to give you a hint for now, but the next one I will not give you. For now, I'm going to give you a hint. We use the first wave equation. C is equal to F lambda. So if this one is like that, then that one is like that. What is C? Speed of light in vacuum. 3.0 by 10 power 8. F naught is the threshold frequency. Lambda naught is the threshold wavelength. So you have been given this one. You've been given lambda naught. 0.45 by 10 power negative 6. Then C is 3.0 by 10 power 8. Now you are asked to get F naught in this question, threshold frequency F naught. See, that one is now simple, you can get. So you are going to calculate that. You can proceed and calculate it and get the answer. Then part B, the work function in EV. The work function in EV. How will I write EV? What does this mean? The work function in EV. What does this EV now mean? This one means electron volt. So you try it. In our next lesson, we are going to explain the meaning of electron volt. What does it mean, and how do we convert from joules to electron volt? I just want to give you maybe some insights. Electron volt is a unit of energy. It is also a unit of energy. We are going to look at, in our next lesson, we will look at what is this unit and why is it there in this topic. And then thirdly, we have a question here. And then it says like this. The maximum speed, you are required to calculate the maximum speed with which an electron is emitted if the frequency of the radiation is 7.5 by 10 power 14 Hz. So take H to be 6.63 by 10 power negative 34, and then M of electron, also that one, take it as, of course, 9.11 times 10 power negative 31. This one is joule second, this one is kilogram. So you take those ones, those are additional information given. The maximum speed with which an electron is emitted. So I want you to take your time to try out this question. When we meet tomorrow or the next lesson that we are going to have in our third lesson of this topic, we will start from here and we will see what answers you got. That marks the end of our lesson today, and I want to thank you, those who joined us online. I hope that you enjoyed our lesson. If you have any questions, if you have any comments, you can send us a text message, you can give us direct call, or you can drop a comment on the comment section. We will go through it, and I promise you it will be acted on, and you will be fine. So thank you so much, and may God bless you.